Today we're covering the midsegment theorem. Now this applies to midsegment of a triangle. They use a nice figure in there to show it, so I'll pull that up. If you're given a triangle and you connect the midpoints of any two sides, you get a new length, in this case DE, that is both parallel to the opposite side and exactly half its length. So when we connect the midpoints of AB and BC, we get a line that is parallel to AC and half of its length. So let's use this first to solve some problems, and then we'll work on some proofs for how it works. The first problem they give us is a picture of a roof truss. And in this case, they tell us that UV and VW are both midsegments of RST. See, a triangle actually has three possible midsegments because you're connecting pairs of sides. And so UV would be one of RST, VW would be the other, and UW, which is not drawn, would be the third. Now they tell us that UV and VW are midsegments, and they want us to find the lengths of UV and RS. So UV, being this midsegment, is parallel to RT and exactly half its length. So if RT is 90 inches, what is the length of UV? Got to be 45 inches because it's got to be half of that 90. Now, they want us to find the length of RS, which is from this point to here. Now, WV is the midsegment that's parallel to that, and WV is half the length of RS, which means that RS is twice the length of WV. So if WV is 57, then RS is twice WV, which means that RS is 114 inches. In the next example, they give you the picture of a kaleidoscope. And they tell you that in the kaleidoscope, AE is congruent to BE and AD is congruent to CD. Show that CB is parallel to DE. So AB, or AE is congruent to BE. Well, if AE is congruent to BE, let's make a little mark here. What does that tell us about E? That makes E the midpoint of AB because it's exactly halfway between A and B. They also tell us that AD is congruent to CD. These two are congruent, which means that D is the midpoint of that side. So DE is a midsegment because it connects the midpoints of two sides. And since it's a midsegment, it's parallel to BC or CB by the midsegment theorem. That's what they're looking for. All right, now we're going to learn a new type of proof today, which is going to make the fans of algebra happy. And it might make things a little easier for those of you that aren't fans of algebra, but we'll see how it works. So part of using coordinate proofs, which is what we're covering today, is placing our figures in the plane in a way that makes it easy to use algebra. So the first thing they want us to place is a rectangle. Now a rectangle has all 90-degree angles. And so if we're going to place it on the coordinate plane, we want to look for a 90-degree angle that's already there, which is right here. That's a 90-degree angle. So we're going to place one of the corners of our rectangle there, and then we're just going to let it extend out wherever we want it. It doesn't give us a specific size, we just draw a rectangle. And then we need to label the vertex, the vertices, the corners. Now obviously this coordinate is 0, 0. This coordinate has a y value of 0. We need to assign some variable to its x coordinate because we don't want to just say it's true for when x is 9 or 10 or whatever value we got there. We want to work with a variable. So we pick a variable. Let's use C for corner, I guess. Now, let's look at this one. This one has an x value of 0. It needs a y value, and we want to put a variable there. Let's call it k, also for corner because, we can't spell. So that means that this corner, since it's a rectangle, this corner has to have an x value of c because it's got to match the one below it. And it's got to have a y value of k because it has to match the one to its right. So there's our rectangle. Now let's try with a scalene triangle. Now scalene triangles are tricky because they don't have any right angles. They don't have anything real special about them. So we just want to place or create our triangle so that one of our sides is on an axis. And believe it or not, the easier one to use is the x-axis. So we'll place a side here, and then we can just draw a triangle however the heck we want. You can make it obtuse, or usually if you're going to make it obtuse, you want the obtuse angle up at the top, like this. So obviously this one's 0, 0. Our x value needs to be a variable. Let's call it t. And then our y value is 0 because it's on the x-axis. Now, for our last vertex, since we don't know how those coordinates relate to the other two, we have to fill those in with random variables. Since we put t at the other one, let's call this r and s. That's how we'd place it. Now for example 4, they want us to use an isosceles right triangle. Now, here's the thing about isosceles right triangles. If it's got a right angle, that has to be the top angle. That can't be the angle, can't be one of the base angles, because then the base angles are congruent, and that would make 180 degrees. So that means that it's got to be our top angle, so our isosceles, or our congruent sides in our isosceles triangle, are going to be going along the axes here. So we want to put our right angle right at the origin, and since this is an isosceles triangle, these two sides have to be congruent. So if this is 0, 0, this has got to be some variable t, 0, and since this other side is the same length, it's got to start with 0, but it's also got to be t units in length. So both of those lengths are t. Then we want to find the length of the hypotenuse and the coordinates of its midpoint. Now, we know how to find both of those because we have a distance formula, which we can use to find the length of our hypotenuse using the 2 points at the end. So we'd have t minus 0 squared and 0 minus t squared. Now t minus 0 is just t. When we square it, we get t squared. 0 minus t is negative t, but when we square that, we get t squared. So total, that gives us 2, or radical 2, t squared. And if we remember our rules for simplifying radicals, I can split that into radical 2 times radical t squared, and the square root of t squared is t. So the length of the hypotenuse is t radical 2. Now for the midpoint, we use our midpoint formula, which says that we add our x's, which is t and 0, and we divide by 2. And we add our y's, which is 0 and t, and divide by 2. And so for our midpoint, we get t over 2, t over 2. Give a second, there it goes, caught up. Alright, so we're going to use a coordinate proof to prove the midsegment theorem. Now, we can't use a special triangle. We need to show this works for any triangle. So let's just draw a random triangle, put one line on the x-axis. We'll make it big enough to see everything in. And we label our points. Now we know this is 0, 0. And this will be Q, 0. And up here, we'll call this one AB. Okay, so you should see that this looks a lot like the last scalene triangle we did here. We just made it a little bigger and changed the letters a little bit. So what we want to do is we want to construct a midsegment and show that it's parallel to the bottom side and that it's half the length. Now, the easiest one that's going to be shown to be parallel is a horizontal one in here. That way we can show it's parallel to the horizontal line just by making it horizontal. So the first step is to find our midpoint. Now, let's label these vertices. Call this A, B, C. So we want to find the midpoint of these two sides, D and E. So we use our midpoint formula with A and B. A plus 0 over 2 and B plus 0 over 2 gives us A over 2, B over 2. And for E, do the same thing, only we got A plus Q over 2 and B plus 0 over 2, which gives us A over 2, A plus Q over 2, B over 2. Now, first of all, we want to show, we can say that's parallel. You could use your slope rules if you want. We know the slope of this side is 0 because all horizontal lines are 0. So AC has a slope of 0. To show that's true with D and E, we could use our slope formula, which says we take the difference of the y's, b over 2 minus b over 2, and we divide by the difference in the x's, a plus q over 2 minus a over 2. Now don't stress about the denominator too much because on top we have 0. On the bottom we'd have q over 2, but that doesn't matter much because 0 divided by anything is 0. So it also is a horizontal line, and so those two are parallel. That's half of the midsegment theorem. The other half is to prove that they have the same length, or prove that the length of DE is half the length of AC. Now we know the length of AC is from 0 to Q, so that's Q units long. So let's use our distance formula to find the length of DE. This is where it's going to get a little messy. So the length of DE is equal to square root of the difference of the x's, a plus q over 2 minus a over 2 squared, plus the difference of the y's, b over 2 minus b over 2 squared. Now, a plus q over 2 minus a over 2, they already have common denominators, so I'm subtracting the numerators, a plus q minus q, or sorry, minus a, I can't read my own handwriting, which is going to give me q over 2 squared, and b over 2 minus b over 2 is going to give me 0 squared. So now I've got the square root of q over 2 squared because 0 squared is 0, and when I add that in I get nothing. And the square root of q over 2 squared is just q over 2. So that's exactly half the length of AC. So we prove they're parallel. We prove that DE is half the length of AC. That's what we need to prove the midsegment theorem. So we're done. And if you have any questions, feel free to ask. You can go back and watch the video again if you need something clarified, or you can go ahead and move on to your homework.